Well, this is the last of the videos discussing electrophilic aromatic substitution and nucleophilic aromatic substitution. We're going to cover quite a bit in this video. We're going to be finishing up the story on EAS, not looking at the different electrophiles that we attacked. That was the first two videos, and not looking at having a single group on the benzene ring as we run in EAS, but looking at how to put multiple groups on the benzene ring and how those multiple groups on the benzene ring would affect an EAS. And we'll close with just a brief discussion of when we flip things, when we have the ring not be the attacker but the attackee, where the ring is being attacked by nucleophiles. So let's go ahead and look at the substituent effects if we have more than one group on the benzene ring, multiple groups on the benzene ring. So not just Y but XY or XYZ. Where do we put the electrophile if we have two or more groups on the ring? Well, here are some rules to use. First, prioritize based on activation effects of the groups. Strongly activating groups are more influential to where things go than strongly deactivating groups. So we try to find activators. Those will determine where the electrophile goes over deactivators. So in that way, then, orthoparadirecting groups, since we have the orthoparadirecting activators and deactivators, they always beat metadirectors because they're either the greater activators or least deactivating group. And we always want to go with those, the ones that are most activating of all the groups, or at least, if you don't have any activators, the least deactivating. So orthoparadirectors typically beat meta-directing groups. So if we had an amine NH3 versus an alkyl group, the amine would be the greater activator than the alkyl group, so it would direct where things go. The bromine versus the nitro group, the bromine is an orthoparadirecting deactivator. This is a meta-directing deactivator, so the bromine would determine where things go. Now sometimes these groups can work together, but if they do not work together, to send the electrophile to the same place, we go with the greater activator or the least deactivating group. And in general, I use never always, but in general, place electrophiles at positions, or sorry, never place electrophiles between two substituents that are meta to each other. So in a gap where if Y was here and X was here, we typically, I shouldn't say never, typically don't go between them. So let's go ahead and look at an example problem. If we have a carboxylic acid group, we want to tag this, and a methyl group. We want to tag these first, do structural analysis, so to speak, and then determine which one's going to direct where the electrophile goes. So this carboxylic acid group has an atom connecting the group to the ring that's in a pi bond to a heteroatom. So we'll just put meta directing for this group. This directs, it's a meta directing deactivator. I guess I'll put DA, it's supposed to be DACT, and I'll maybe switch to a smaller pen here. So a meta directing deactivator, and the alkyl group is just a weak type of orthopara directing activator. So we have done the analysis of the two groups off the benzene ring. One's an activator, one's a deactivator. Well, right there we know this one is going to have the greater influence. It tends to send things to the ortho and para positions. Now the para position here cannot be reacted with because we have no proton here. We have a group there sort of blocking this from being used to attach the bromine or Br from Br2 and FeBr3, but we can use the ortho positions. Now these two groups are then in this case working together because this group is a meta-directing activator, which is also favoring these two positions. So these two groups are not competing against each other but are pushing the electrophile to the same position. So we know FeBr3 and Br2, or iron and Br2. We have halogenation using, if we can, just to draw the salt that you would have, or that we can propose as practically getting us to the product. We can say these bromines start interacting with the iron and either go to a full salt, as shown here, where one bromine is with this iron, or we have a complex, a ion complex. But we're going to go ahead and draw it as the salt so that we get an idea of what happens. The Br plus is attacked by the pi electrons to put the bromine at the ortho position to the greater activator, that methyl group. And that just simply was also, I guess, not working against this carboxylic acid group, but the carboxylic acid was sending it to the same position. But again, if that was not the case and this was at a different position, we go with the methyl group as deciding where the bromine goes. And again, we just need to make sure we know how to tag those groups. This one was the greater activator. Alright, well, that's all that we need to talk about when it comes to multiple substituent effects, having more than one group on the benzene ring. Now let's talk about putting multiple groups on the benzene ring. Well, if we wanted to take benzene and we wanted to make 4-bromo-benzoic acid, how would we do that? Well, we can look at things synthetically, working from left to right, and we'll do that with this slide. And then on the next slide, we'll look at retrosynthetic analysis, where we switch the positions. The product is shown first, and we work back to the reagent. So these reactions in general, multi-step reactions, often require that you string together, I guess, various reactions from various chapters and notes. In this case, we'll stay within the set of notes on EAS to provide or propose a viable synthetic pathway, I guess, synthetic pathway. So how can we make that p-bromobenzoic acid using benzene as a starting reagent? Well, we have really two, I guess, things to do at the beginning point. We can either start trying to put the bromine on and then worrying about this group later, or trying to put not a carboxylic acid group on, but at least a carbon here that we can oxidize later on to carboxylic acid, trying to put this side together first and then put the bromine on. So it really starts off with alkylation, which is going to then, and it's later on in the reaction, be oxidized to a carboxylic acid, or halogenation. Really, those are our two starting points. So we can look at it synthetically and say, I'll put the carbon that I need on by doing alkylation, or I'll put the bromine I need on by doing bromination. So we could do that, and this would give us an ortho-para directing activator. This would give us an ortho-para directing deactivator. So after the first step, we could still put something at this position for both structures as, I guess, their first product in the first step. For both of these, we can go on and put a group of bromine across from this methyl group, or we can put an alkyl group across from this bromine. Now, some things to note here: this is an activator, so that can be a problem if we are trying to just make mono, I guess, substitution product. Well, this could go on to have alkylation, because this is more reactive than the benzene ring. So we can have problems in this synthetic pathway with disubstitution, making maybe a 1,4-dimethylbenzene, 1,4-dimethylbenzene. And that's not seen in this reaction here. We can favor mono substitution because we have a deactivating group on that would cause this ring to be less reactive after it's been brominated, and this would continue to make more mono substitution product. But what's interesting is that if we go on to the next stage for this pathway involves a deactivating group where we're trying to do a Friedel-Crafts reaction. So we may have some problems in the second step here where things were good in the first step, and we may have problems in the, I guess, a good thing in the second step on this top pathway, but we had some problems maybe in the first step. So there can be some arguments made for why we'd want to run both of these. So they're both looking to be somewhat viable. We haven't broken the rules for Friedel-Crafts. We can do Friedel-Crafts reactions. We can do Friedel-Crafts if we have something other than a meta-directing deactivator. At least there's a chance for it. We cannot do Friedel-Crafts reactions, alkylation, acylation, if this is a meta-directing deactivator. You just cannot do it. So it may be hard here but we have a chance to have a Friedel-Crafts alkylation. So I could add methyl chloride and aluminum trichloride to have the, flip this, apologize, we flipped this over. So we just have alkylation at this position across from the bromine, a methylation, I guess, using methyl chloride and aluminum trichloride on this bottom synthetic pathway. And in the top, since we have our toluene, we have the methyl benzene. We added Br2 and FeBr3, and we can have halogenation of the para position. Now I'm not drawing the ortho, I guess, substitution products, which we could have mixtures with. This para substitution product plus the ortho. And the same way here, we have an ortho para directing group. We have plus the ortho. But we could say we have a viable way to make the para product, a para bromotoluene or para bromotoluene down here. We're at the same point. So here we see after 2 steps in, from benzene, we can take these 2 different electrophilic aromatic substitution reactions and put them in different order, and both are viable. Now at this point, we have to oxidize this methyl group to make carboxylic acid. And on a previous video we said just know, not the mechanism for this reaction, but just know the oxidizing agent KMNO4 followed by addition of acid can be used to oxidize any alkyl group wherein this carbon connecting the alkyl group to the ring has at least 1 CH bond. So we have that, of course, three CH bonds, and we can make carboxylic acid groups from a methyl group. So we finished this in the same way, where in the first 2 steps we had flipped the EAS reactions. Both are viable and would be considered for a use in the lab. Now that's working synthetically, working from reagent to product. We can, and I'm going to go ahead and kind of hide some things here, we can try to work retrosynthetically. This is very valuable because we may have a desired product and we have to propose how to come to that desired product, working, I guess, all the way back to starting reagents we might have on supply. In this case, we're going to consider benzene as our starting point and this as our final product. And we're going to work backwards. So M-bromo benzoic acid, how could we make this? Well, the thing you probably want to do is to make sure to tag these groups to kind of know if I have it on, how would that affect any other EAS reactions. So this is an ortho-para directing deactivator, we know that. This would be a meta-directing deactivator. So if I put this on first, kind of thinking backwards, if I put this on first, I could only have something go to the ortho or para positions in the EAS reaction. But if I take and put this group together first, then this would direct bromination to the meta position. So in looking backwards, what I'm thinking I'm going to do is go ahead and have this as our last step. I'm going to propose halogenation of benzoic acid. So that's our top route. We're going to start, I guess, proposing this backward action. I could say I could have had my last reaction be bromination using Br2 and FeBr3 if I have benzoic acid. Now, along with that, we could also consider our last step to have been this oxidation of the methyl group to the carboxylic acid. But we're going to have to maybe see the problem here of methyl group with a bromine. These are both ortho-para directing, in one case activator, but they're both ortho-para directing. This is an ortho-para directing deactivator. So we cannot, just in the next step going backwards from this point, we cannot propose to have one of these on and put the other one on as is. Something would have to change here. But here, I think we're doing much better. We have one group on. We've halogenated to put the bromine on, and we can propose, working backwards, how we could have made a carboxylic acid group. We could have had the oxidation of a methyl group. So we're going to expect to see KMNO4, or potassium dichromate, as an oxidizing agent that would be used having a methyl group here. And so we can certainly see that. We can say a methyl group could have been oxidized to this. So we're again working with retrosynthetic arrows, which is fatter arrows, and we're going from, and this is not usually drawn from left to right. They usually draw these from right to left, but they use these fatter arrows which tell you that you're working retrosynthetically, you're working backwards. So we could say, hey, if I would have had this, I can oxidize to carboxylic acid, and having a carboxylic acid, a meta-directing group, I can halogenate to make my final product. So how are things going on the bottom here? Well, this here, if we put the bromine on, we cannot add just methyl chloride and aluminum trichloride and expect that group to go to the meta positions in the end, and I apologize, I moved this a little bit. We can't expect these two groups to end up meta to each other. Why? Because this is orthopara directing deactivator, orthopara directing, and if I try to run alkylation reactions, it's going to send it here, ortho, or here, but not here. So this is not going to work. We just cannot run this bottom route. So we cannot say both pathways are viable. Both pathways are not viable. Which one will not work? Well, this one will not work, because the bromine, if on, as is, we cannot just add an alkyl, an alkyl group by alkylation, or cannot substitute through alkylation. We cannot do that because it's going to send it to these positions that are marked with the X, not to this position that's meta to the bromine. That won't work. So this pathway becomes, invalid. It's not going to work. This one is still a viable method, and we can easily propose how to make methylbenzene by just having benzene and our methyl chloride and aluminum trichloride in the alkylation reaction to start things off. So that's working retrosynthetically as compared to working synthetically. And again, I drew it kind of from left to right, but apologize. This is how you would see it. You do see the retrosynthetic arrows are just bigger, and so we can work from product back to reagent in a left to right manner or whatever. You just need to notice that if they show the product first, you start seeing some fatter arrows that are showing a retrosynthetic move from product back to reagent. And we had contrasted that with working from reagent to product. This is working synthetically, just proposing from left to right reagent to product, or working from left to right product shown first, going back to reagent. That's working retrosynthetically. Right, just two more slides. We need to cover, as we close this video, we need to cover nucleophilic aromatic substitution. So in EAS reactions, the benzene ring starts things off by acting as the nucleophile. Well, things are flipped in the NAS reaction. In the NAS reaction, the benzene ring is attacked by a nucleophile. So we have two ways we can do that, sort of a benzyne-mediated reaction and a nucleophilic aromatic substitution reaction, also known as SNAR reaction. For the SNAR reaction, we need two things. We need a leaving group, and we need a strongly withdrawing group, electron withdrawing group that's strongly electron withdrawing, a nitro group, a carbonyl, something that has withdrawing effects by resonance. So we need two things for SNAR, a leaving group and a strongly withdrawing group, electron withdrawing group. And in most cases you'll see some sort of strong base added to this solution. Not always needed a strong base, but often a strong base will be used in the SNAR reaction. Let's walk this out mechanistically. So we take our strong base, and again, it's not always a strong base, but you typically see them used. And we're going to attack the partially positive carbon made such by the electron withdrawing group. The electron withdrawing group is already pulling on this benzene ring, but from particular positions. The ortho and para positions to this nitro group are partially positive. So we can come in and attack that carbon that's partially positive, advance the electrons up into the electron withdrawing group to get an intermediate, or non-aromatic intermediate. Now, it's not the same intermediate we have with EAS. We have a negatively charged species. This is positive and two negatives, so we have overall a negative charge intermediate that's going to kick off the chlorine to reestablish aromaticity and create a more stable anion. In most cases, you'll have a strong base to weak base transformation, where that strong base is now added or substituting out that chloride. So a strong intermediate is formed that's non-aromatic, and then we kick off the leaving group in the second step. That's just a SNAR mechanism, where the halogen in the end is replaced by that nucleophile that's added to the chlorobenzene with a withdrawing group somewhere at the ortho or para positions relative to that leaving group. So we have to have those two things for SNAR. Leaving group that's going to be substituted out, and an electron withdrawing group at the para or ortho positions to this carbon, either next to or across from that carbon that has the halogen. Alright, one last way to have nucleophilic aromatic substitution is through, I guess, the benzyne mediated pathway, or what's called an elimination addition reaction, where we don't have anything but just a leaving group. We do not have the electron withdrawing group. It's going to require a stronger base. If we have no electron withdrawing group, it makes sense that we're going to need a little bit more power in the nucleophile that's trying to sub out this chlorine. And the mechanism is a little bit, I guess, different from anything you've seen. What we're going to do is we're going to take, well, I guess I shouldn't say altogether different, but it's going to force us to make what's called a benzyne. So we have a strong base that we're going to kick things off with, but it's going to act not towards the carbon. This carbon here is not very reactive. We don't have any electron withdrawing group making this, I guess, greater and partial positive charge than what we have here, just with a little bit of effect of the chlorine. So it's hard for it to come in and attack as a nucleophile. It tends to come in and attack as a base. This very much more reactive, stronger base acts as a base and makes what's called the benzyne intermediate. Very unstable, the benzyne. This benzyne has some resonance wherein the pi electron that's strained here, this is a strained triple bond because it's triple bonds are usually in a linear, I guess, structure, not in a cyclic structure. This is a strained triple bond. So what happens is some of the pi electron density just sort of dynamically is moving to one carbon or the other into a lone pair and leaving a positive charge at the other carbon. So you tend to get some, I guess, expression of polarity within the benzyne. Well, that can open the door then for another equivalence of the sodium amide to come in and attack one of those carbons, because again, this is not a non-polar triple bond. No, there is some polarity because it's so strained. It'll start to stack up on one side or the other, creating some partial charges. So we can attack one of those carbons in this benzyne, advance the electrons up to a lone pair state, which is going to be very reactive. So we're still going to have one of those pi bonds left, but we've broken the, I guess, triple bond by taking one of the pi bonds and moving it up towards this carbon in a hybrid orbital. So there's a very reactive lone pair here, and we're going to finish things off then with the ammonia that we made in the beginning, or ammonia that's in the solution, is going to act as a proton donor. Not a very acidic proton, but this is a very, very strong base. Very, very strong base that's made in solution. So we need to have some sort of acidic proton strong base. Some acidic proton, and we do have that if you add with the sodium amide just some ammonia, you get sort of a buffer solution. And we can have then our proton given back to that carbon that we took a proton away. We're going to give a proton back. We're going to have our NH2 group, and we'll have reformed our initial sodium amide. We can kind of follow that sodium amide if you wanted to do, I guess, accounting of to balance this reaction. We use one amide to tear a proton off, but we give that proton back. So really what we're consuming here in this reaction is the amide, sodium amide, one equivalent. We're going to regenerate one equivalent back in the reaction. So that's the nucleophilic aromatic substitution through the elimination addition mechanism, or the benzene mediated reaction. This is the key intermediate, the benzene, wherein that triple bond in the ring is very unstable. So we had this sort of polarity that you can get with that strained or that weakened pi bond, where the lone pair can stack up here and have a positive charge here, and it drops back down, moves to the other side. So there is a little polarity dynamically with this benzene, and we can, I guess, key in on that. We can make use of that by attacking one of those carbons in that triple bond. Well, that's it. Kind of a long video. I'll stop there. Bye-bye.